All right, physical science time. Let's talk today about, let's label this, we could call it energy to, let's call it energy transformations. Oh, I've gotten really carried away with my letters. And calculations. That kind of rhymes, so it sounds nice. Energy transformations and calculations. Let's do write the objective down. Students would be able to, it says describe, calculate, and model energy and its changes. Describe, calculate, are you writing the objective down as I do?
Yeah.
Describe, calculate, and model, what's the rest of it? Energy and its changes. That doesn't seem too difficult. Energy and its changes. Yesterday we correctly defined energy as the ability in the universe to do what?
Change.
Yeah, to cause change. The ability to cause change. That's such a fundamental thing. You see what this is important not only in every science, but in every single facet of human existence. This is an important concept because all our life is change. The only thing that's steady about your life is that it will change. That's it. Everything changes, and the stuff of the universe that causes the change is energy. It's always energy. Always some energy has to be created and destroyed? No.
It can be created or destroyed.
Yeah, energy cannot be created or destroyed. So, what is happening when energy causes change? It doesn't get created or destroyed. It what?
Transform.
Yeah, the energy itself changes. The energy transforms. We talk about, I draw this distinction between what I call, or what your book calls, energy transfers and energy transformations. Let's talk about those first. Energy transfer and energy transformation. What's the prefix here that's in common between these? What's the prefix trans mean? Yeah, what's that mean?
Change.
Not quite. Well, sorry. What other words do you hear trans in? Transgender. Transportation. What else?
Like transportation.
Yeah, we said transportation.
Transform.
Transformers. I think of the word, I don't know if you're aware of this word, but transvestite is someone who cross-dresses. A transgender is someone who crosses from one gender to another. Transportation is being carried from one place to another across.
So always a change.
Yes, it's always, well actually what it is cross. This suffix or this prefix trans means cross. You've heard of trans fats?
Yeah.
Without getting too deep into chemistry, fats are they're large molecules like that, and if a certain group, I don't even know what it is, I think a hydroxyl group, is here and here, they're across from each other, and so that's called a trans fat, whereas if they're on the same side, it's called a cis fat. These are supposed to be bad for your heart health. I don't know, the science is kind of loose on dietary things like that, but the word trans means cross. So what's crossing here? An energy transfer and an energy transformation? Well, first of all, energy transfer, I like to draw the distinction that this is when the object I don't really want to say has the energy, but the object involved with, that's not even very good. The object related to, let's put that, the object related to the energy changes. This is kind of I shouldn't have phrased it this way, but I already did. So what is changing here in this sentence? Just looking at the sentence, what's changing?
The object.
The object, exactly. Interestingly, the verb in the sentence is change. The subject of the sentence is the object, which is kind of funny because subject and object are different things in English. Anyway, the object is changing. So perhaps, let's an example where, let's think of thermal energy. How could thermal energy change from one object to another, but still be thermal energy?
Like
Yeah, like if you got a hair dryer and the thermal energy is moving from the hair dryer to your hair, that's an energy transfer. The object where the thermal energy is changing.
Or like a heating lamp?
Yeah, heating lamp. I use thermal energy. What's a way that electrical energy could transfer?
Right from an outlet.
Yeah, from the outlet where there's electrical energy to your laptop where it's still electrical energy. It's just moving. The energy is moving. It's an energy transfer. Whereas an energy transformation is the type of energy changes. So what would be an example of an energy transformation?
Like heat to cold.
Yeah, cold's not really energy. Cold is just the lack of heat energy.
Wood.
Solid to a liquid, maybe?
That's matter. That's different from energy, but that's a good guess. So we just had two examples. One was
mechanical to electrical.
okay, good. So yeah, mechanical to electrical. We can use something called a generator that changes the mechanical energy of a turbine. It spins, and then that causes electrical energy to be generated. And that would be mechanical energy, which is the energy of motion, or it can be the energy of motion, changing to electrical energy, which is a whole different type of energy. Probably still within the same object, not necessarily, but probably still. God bless you. So speaking of types of energy, let's list over here, not really a side note because we do need to know these, but what are some types of energy? Well, we said several already. Let's say
Mechanical, chemical.
okay, hold on, let's slow down. Mechanical energy.
Chemical.
This, I'm going to write down that the mechanical energy is potential energy, which we talked about yesterday, yeah?
Mm-hmm.
Plus kinetic energy. That's called mechanical energy. You need to write that down. That's all the dang over your test. Mechanical energy is potential energy plus kinetic energy. Together we call those two things mechanical energy. They're the energy an object has because of its position or its motion, which are similar because of the energy an object has because of how it is, how high it is, how fast it's moving. Okay. What's another kind of energy? We did some of these yesterday too.
Chemical.
Yeah, we had several types of potential energy. We had chemical. I'm abbreviating PE. Once again, what's PE stand for?
Potential energy.
Yeah, we had chemical, elastic, and the other one was gravitational.
What was our definition of energy? Energy is a change.
The ability to cause change. The ability to cause change. Just as help up and shut the door, please.
Gravitational?
Yes.
Do what now? Door.
Okay, what other kinds of energy are there? We had kinetic energy, obviously, so we'll put that one there. And kinetic energy is the energy an object has because of its motion. I love that we can remember that kinetic energy is from motion.
Kinetic energy.
What? Have you ever heard the word kinetic before?
Yes. Kinetic sand.
Kinetic sand that moves. Yeah, what?
In like 6th grade, we had this game where it was like a hockey game where you had to find out the kinetic energy that the hockey was.
That's cool.
We just unlocked
The
a secret.
word cinema. You've heard the word cinema. What's that mean?
Like a
Like a
movie
The movie. It's the movie theater. The word cinema comes from the same word as kinematics, kinetic energy. They both have to do with moving. The cinema is called that because of the motion picture, right? The picture is moving, so it's called that. It has the same root word. Also, I think about some video games I'm aware of if you have weapons, and then some classes of weapons are considered kinetic, which is where that means that the weapon is doing the damage it does because the projectile is moving fast. In real life, guns exhibit kinetic damage because they're hurting a deer or a dog or a lizard or whatever because of how fast the bullet is going. That's kinetic. Yes.
What was our chemical one? What was that?
Chemical is a type of potential energy. What are some other types of energy besides mechanical?
Thermal.
Yeah, thermal. And what's that one? Let's just put it right next to it. Really simple, one word. Thermal energy is the energy something has because of its
Heat.
Good. We shouldn't have a problem on that one. If you need a hint, think of a thermos, which has the same root word as thermal, and that keeps, or a thermostat. Status meaning or status meaning the same, so it keeps the temperature the same. That's what a thermostat does. Thermos keeps your cold beverages cool, your warm beverages warm. Thermal underwear is supposed to keep you warm. What's up?
How does a thermal scope work?
A thermoscope? A thermoscope is what tells the temperature of an object. It just uses infrared radiation, which is a way of measuring heat. We'll talk about that
Which
much
is
later.
why, like, if you play, like, Hunger All the Wild, you probably don't have that on there, but
I don't
you have a
know
little
what
thing, like, zoom your scope, and you press
It's like
it.
a hunting simulator.
Yeah,
Cool.
hunting simulator.
Okay. What other kinds of energy are there? There are more. We said one more for sure.
Electrical.
Yeah, electrical. Electrical. What others?
So we have mechanical, chemical, thermal, electrical.
Potential.
Now we are.
Yeah,
We have all those. I'll just put a few more down here. We have
Joule.
Joule is the way we measure.
Oh.
In fact, this is probably good for now. Let's just, there are more, but we'll just consider that was finished for now. Let's talk now about how we calculate these things. Specifically, we're going to calculate these two things. We're going to calculate GPE. What do you think that stands for?
Gravitational pull energy.
Gravitational, one of you got it right, potential energy. I usually abbreviate this, the professional way is to abbreviate U. And at some point, the letters stop standing for things and that's just a symbol for it as opposed to what it's actually starting with. But U equals, what's U equal to? By the way, remember we just talked about this, gravitational potential energy. So U equals mgh, where U is, remember we talked about equations, it's been a little bit of time since we've done one, but what I'm going to do now is I'm going to say what each symbol stands for. What do you need? Why do you need to know this equation? What are you going to do every single time?
Math.
Find the...
No, what do you have to do every single time you have a problem with this?
Write the raw equation.
Write the raw equation. This is the raw equation, so write it down.
Sandwich.
Write it down. Yeah, this is the Arby's dang sandwich. This is bread layer 1. What's up?
What type of, so like how we wrote down mechanical energy equals potential plus kinetic,
Yeah,
and then chemical is a type of potential energy.
Yeah.
What would electrical be?
that's a type of kinetic energy because it has to do with the motion of electrons. Anyway, U is, we just said, gravitational potential energy. Gravitational potential energy. I'm just abbreviating this because I already wrote it 15 times. And what do we measure energy in? We're going to talk about that in a second, so leave it blank. Lowercase m is
Mass.
mass, measured in the SI, kilograms. Lowercase g is, you remember this? This is from a...
Gravity.
Yeah, it's the acceleration due to gravity, so let's make sure we put that, but you're right. Acceleration due to gravity. If it's an acceleration, what do we measure it in? Should remember this.
Newton's.
No.
Meters
you.
per second squared.
Meters per second squared, thank you. And then h is
Height.
height. Good, thank you. And what do we measure height in the SI?
Meters.
Meters. So if we multiply together, look, see, these are all just multiplying. We're going to multiply mass times the gravitational acceleration times height. So we're going to multiply together for the unit. We're going to multiply together kilograms times meters, meters per second squared times meters again, which makes that what? Meters times meters is
Meters
squared.
meters squared. So now we have kilogram meters squared per second squared. That's not a Newton. Remember, a Newton was kilogram meter per second squared. That's a Newton. But this one is a Newton times a what?
Meter.
Yeah.
Squared.
So this one equals a Newton, no, just times a meter, which is equal to a different abbreviation that we have, which is a joule. Capital J-O-U-L-E. The abbreviation is J. So what do we measure gravitational potential energy in? Joules. Too cool to joule in school, or at least in school.
Okay.
It's still outside of school. You're like, I'm gonna joule it, and then that's how you talk from then on. You're like, give me another joule, mom. The joule will kill you, but it does use energy transfers. There's a little boy in there that battery, electrical energy. Actually, the battery is storing energy as chemical potential energy. And then as it releases that energy, it has electrical energy, which warms up a little thermocouple, which is thermal energy, and that boils poison that then you inhale, and then you poison yourself. Okay.
How do you know so much about that, Mr. Knapp?
I know almost everything about everything. Okay, except for sports. That's why I'm able to know so much, because I know almost nothing about sports. I don't waste my time with that, and so I know all this other stuff about, I guess stuff that's just joules. Joules, exactly. Okay, so... let's do one of these real quick. Let's use this little guy as an example, which you cannot see. It's a secret. Do not say its name. Do not mention it to the people who cannot see it, okay? Okay.
What is it?
We're trying to find the gravitational potential energy of it.
It's a little about
What's its mass? We're going to give them some hints. What's its mass? Probably. Just guess.
I don't know.
I don't know,
Like,
maybe a pound.
like a kilogram.
Yeah, we'll phrase it like this.
2 pounds.
It
Like 2.2 pounds.
is.
It's probably 1 pound.
2. Oh yeah.
There we go.
People, right?
It
It's probably
is on a shelf.
8.
We'll say 2 meters. 2 meters above
Not talking about
the ground. It has a mass of 1.3 kilograms.
Oh my. Is that real?
No. I don't think it's probably that heavy. Has a mass of 1.3 kilograms. We don't always have to mention this, but I should say, to be specific, I should say, this is on Earth's surface. It's assumed that that last line is true. If it doesn't say that, assume it's true. Why is that important for this equation?
Because
You guys have the gravity.
Yeah, the acceleration of gravity would be different on different planetary bodies. And so we should technically put that, but if it doesn't say it, assume it's on Earth's surface. By the way, not only do we know on Earth's surface that g is acceleration due to gravity, we don't just know...
Say goodbye to that.
You step on the lips.
See you, buddy.
Yes.
We don't just know the unit is meters per second squared, we know its value. What is its value? So you can count. 9.8 meters per second squared. Please write that down. Okay. It is on a shelf 2 meters above the ground. It has a mass of 1.3 kilograms. This is on Earth's surface. What should I do first to solve this problem? I'm going to erase some of this. This confuses people when I do this. So I'm going to switch colors. It's not going to help a lot, but it'll help a little. Write the raw equation. What is it? This little purple is what the little babies would write. So you see this in your book. It probably wouldn't be as cool as I've made it, but you are the purple. Okay? So you write.
U equals.
Yeah, what? We're gonna waste our dang time writing what I just wrote. I just literally erased it. We're gonna waste our time writing it?
Yes.
No, it's important. Every single time, write the raw equation.
Every single time. Right, raw.
Okay. So we've written. It's a waste of our time, isn't it, Cole? No, it is not.
It's an extra point.
It helps us do two things. It helps us know where to put in the stuff we're gonna put in, right? Otherwise, we're gonna do it wrong. We will literally, even those of us who are smart, on the last test, I'm grading these, I'm like, oh, you didn't put your raw equation. Oh, you put all the numbers in wrong because even though you're smart, you didn't know how to put them in because you didn't write the raw equation. And it helps us memorize the raw equation, which is important too. What should I do next? What's the next step?
Substitute.
Yeah, if we needed
We
to.
don't need to.
How do we know? Well, actually, this didn't even say. This should have said calculate potential energy.
Mr. Kine, is Earth's gravity squared? It's 9.8 meters per second squared.
9.8 meters per second squared. The 9.8 is not squared. That's the acceleration of gravity. Anyway,
Sorry.
we're trying to calculate u, so we don't need to manipulate. What's the mass?
What is like 3?
Mathematically, this is very simple. 1.3 kilograms times 9.8 meters per second squared times 2 meters. Okay? Multiply this. So the math part, 1.3 times 9.8 times 2 is going to be roughly 25-ish.
Calculator.
Calculator boy, get it out, but I'm going to put 25 for now. 25. And then our units, just like we would multiply if we had 4x plus 3x plus 2x, I'm sorry, 4x times 3x times 2x, it would be 4 times 3 times 2, which is 24, times x times x times x. We're going to multiply kilogram times meter per second squared times meter. So kilogram times meter per second squared times meter, which just makes that into meters squared. And what did we just say a kilogram times a meter squared per second squared is?
A joule.
U equals, what was it? Was it 25?
He just handed you a calculator.
Okay, it is 25 joules. 25 joules.
Oh, we're...
You're supposed to multiply 1.3
Where had your brain?
9.8 times 2.
Times 9.8
times 2.
times 2. 25.48.
Good, 25 is correct. So, it actually probably should be 26 if you're rounding, but that's okay.
No, it'd still be 25.
But guess what? What's more important here? The 25 or the kilogram meter squared per second squared? Yes, the unit is more important, okay? So make sure that your units, when you multiply them, come out to this, which comes out to joules. That's another way of doing this. If you were somehow thinking enough that you were multiplying the units at the end, but you weren't thinking enough to put your equation in, these units should turn out too. If you somehow divided in there, you'd have a completely different unit, wouldn't you? The units should, if you do this correctly, you should allow the units to be the guide that tells you, oh, my answer is in joules, so that should be in energy. These two things should match. This should be a measure of this. And if it doesn't, or if you just slop it out, then that means you did it wrong, okay? Let's do another one. This time we're going to, well, let's do another one. I should say, did everyone get the first one written down?
Yep.
Did anyone not get the first one written down?
No.
Okay. Let's move on to the next bit. There will be more of those. You'll have to have more practice. Next, instead of talking about all this, we're talking about Can you guess what we're going to talk about next?
Transformation.
No, we already did that.
Calculation.
Calculation of what?
Joule.
Kinetic energy. Yes, which is measured in joules also. Kinetic energy. Okay, so in the same way that we use, your book uses GPE, gravitational potential energy. Professional physicists, and in physics class we use U. Your book uses KE for kinetic energy. Professional physicists, and in physics class we just use K. Here's the equation for kinetic energy. K equals 1/2 mv squared. So this is a little bit more complicated, and why do I say that? What makes it slightly more complicated? There's a coefficient for one thing. What else makes it slightly more complicated?
Squared.
Yeah, there's an exponent. So K is, we already said,
Joules. No, sorry.
kinetic energy, which we will probably measure in joules, but we're not going to put it yet because I want to show you how it works out the same. 1/2 is 1/2. We're not even going to write that. M is mass. What do we measure mass in the SI? Kilograms. And V, sorry, this would be V with an arrow, is velocity. Why? How did you get that so fast?
Because V is velocity.
Oh, V is also volume.
I just knew.
V is also virus. The V stands for all kinds of things.
Because the V has a line above it.
Because it's an arrow.
Yeah, that's not a great way. V also stands for vector, which would have an arrow above it.
Vector!
No, but what? Why do we know that this is going to depend on velocity? Why do we know it's going to depend on velocity?
I have no idea.
What was our conceptual definition of kinetic energy? The energy something has because it is?
Velocity.
Sorry, what was the question?
Motion.
Sorry.
How do we measure motion?
Velocity.
Velocity. Yeah. Okay. What do we measure in the SI? How do we measure velocity?
Meters per second.
Meters per second. Meter per second squared? No. That's what?
Acceleration.
Acceleration. So now check this out.
Check this out.
What are we going to do with the velocity, though? This whole thing gets...
Multiply.
No, it's
Squared.
squared.
Oh, yeah.
So our units will be kilogram. The half, is that going to change the unit?
No.
No, it'll change the value.
Yeah.
If our mass was 14, now it'll be 7. But it doesn't change the unit, so it's going to be kilogram times meter per second. But this whole thing gets squared, so we end up with kilogram times meter squared, right, the square distributes, per second squared. Ah, what is this? What is this? Yeah, it's still a joule. 2 different ways to skin a cat. That we're not skinning.
What?
2 different ways. We had 2 different ways of getting there, but both of these units for gravitational potential energy and kinetic energy end up being kilogram times meter squared per second squared, which is a joule. A joule is thrown from one end of the
Dumpster.
locker room
Oh.
Oh, not the locker.
Not the
to the other. It has a mass of 450 grams. That's too many.
That's a very heavy tool.
You don't know anything.
I don't.
Well, that was really mean, Justice. I'm sorry. You don't know how heavy a joule is.
You don't know
It frustrates
anything.
me because you shouldn't know anything is what I should have said about joules. Let's say it has a mass of 250 grams and is traveling at, we'll say, 1.3 meters per second. Find its kinetic energy. Okay? Now, purple again, that's when you would read in your book. Your book's always going on and on about joule. Purple again is going to be U. I should be qualifying. Joule is not a sponsor of this video. not a sponsor. The ads come up and it's like, hey kids, you like science? Maybe you'll like poison. Okay, Joule. What should I do first?
Like the raw equation.
Tell me it.
M equals
K equals.
Well, we got K equals half mass velocity.
What should you do with this equation?
Solve it.
What should you? Yeah, but we're not getting there. What should you do personally with this equation?
Memorize it.
Memorize it. You need to have this for your test. You're going to fail your test if you don't have this equation memorized. Okay? Do we need to manipulate?
No.
Could we manipulate?
Yes.
Yeah, if we have to. How would we find velocity if we were going to manipulate? We would have to
divide half.
First, listen. First, we'd have to divide half m over, so it would end up being 2k over m. So far, so good. But then we have equals v squared, so what would we have to do to get rid of the squared? What's the inverse of square? Square root. So it would equal, our manipulated equation would be square root of the quantity 2k over m equals v. Okay, anyway, but we're not doing that right now. We're just substituting. K equals, our gram's gonna work?
No.
What do we have to do first? So instead of writing K equals conversion, 250, write your conversion, 250 grams. I'm gonna let you do the rest. What should I do next, anyone?
Have your conversion bar.
Conversion bar. What do I do next?
Grams on the bottom.
Thank you, Rhett. I put grams on the bottom, going to
What are we going to?
kilograms on top. How do I know I'm going to kilograms? Like, he just made that up?
No, you should know.
Yeah, we just said that the mass for K equals 1/2 mv squared. The mass has to be in kilograms. So, and then we think to ourselves, self?
Yeah.
Say
Self what? Self how many grams?
yeah, just tell me though. You don't say self how many grams are in kilograms. You say self in,
1,000 kilograms in
They're
one.
100.
be more careful.
1,000.
No, you're all making nonsense up. Say the whole thing. Raise your hand if you know it. Rhett.
There are 100 grams in a kilogram.
There are 1,000 grams in 1 kilogram.
I said
Okay? So, 250 divided by 1,000 is 0.25. What? 0.25 kilograms. You don't. Once again, I'm not going to say like I was so mean to Justice, but you don't know what this is.
Are you throwing one at me?
This is like 6 ounces. Not huge. What's the mass of... Tell me, what's the mass of your juicy right there? Look at the bottom. Yeah, I was going to say in milliliters, but it's the same. It's mostly water.
Milliliters, 473.
Yeah, that right there is 473. So this is not that big. It's just maybe a little big. This is XL joule. XL joule. Anyway. What next? What next? Thank you. Cool. What next? Substitute. So K equals 1/2 0.25 kilograms. What's the velocity? 1.3 meters per second.
Meters
Squared.
per second squared.
K equals, what's 1/2 of 0.25?
No idea.
Really? That's embarrassing.
I'm sorry, I'm just stupid.
No. Thank you, Fiona. Say it louder.
14 and a half. 13.
125.
Oh yeah, I knew that.
What's 1.3 squared? Well, what's 13 squared?
13 squared is
13 squared is like 130 something.
not 169.
Yeah.
69.
I'm not smart. Ask Rat.
Don't you guys have a
What's
math class here?
69?
Type in your
That's
calculator.
right.
Who's in geometry?
Ask Rat.
Type in your calculator,
Black.
please.
Like what
Come
my
on.
calculator?
Oh, it's off.
69.
Justice.
Yeah, it's
Zero.
So if 13 times 13 is 169. So 1.3 times 1.3 would be
Oh,
It's
69.
1.69.
1.69
Oh, I was
meters
right.
squared per second squared, right?
I was right except I didn't put the decimal in.
K equals, do this math please.
Okay, 0.125 times 1.69, you get 0.21125.
0.21,
1.25.
no, what?
Oh, percent.
Joules.
Well, kilogram per meter squared per second squared, which is equal to 0.21 joules. Blood.
Glug glug.
All right. You have questions about how to calculate the energies. One last thing. This one's the easiest one out of all.
Belly button.
Capital M, capital E, mechanical energy equals U plus K.
We're solving.
This one's more of a thing that we use conceptually. Mechanical energy is just, it's straight up potential energy plus kinetic energy. What you need to realize is that when an object is in flight, let's say,
Like flight reaction.
like a projectile. Let's say Rhett throws the football. This is roughly what a football looks like. I know about sports. And the path is going to be a parabola, as it always is. Yes, parabola.
Yes.
As we're going to negate friction, so we're going to assume there's no friction. In reality, both of them would decrease, and thermal energy, friction, would increase. Real quick, write down friction. Friction is the transformation of kinetic energy to thermal energy. What does that mean? Things go fast past each other, and what do? They instead of keep going fast, they slow down and they get
Kinetic.
they slow down and they get
Friction.
hot. Yeah, they get warmer. They slow down and they get warmer. Friction is
causes heat.
Friction is the transfer, or did I say transfer? The transformation of kinetic energy to thermal energy. So write that down, please. Anyway, for this we're going to negate friction. We're going to say that it's not going to generate any more thermal energy. In reality, both kinetic energy and potential energy would slowly decrease, and thermal energy would increase. But in this case, we're negating friction. So as it goes up, what's true of its potential energy?
It goes slow.
No, sorry, its potential energy. As it goes up, its potential energy gets
Weaker.
Yes.
What does potential energy depend on? Mass? Is that changing? No.
Massive velocity.
The acceleration of gravity, is that changing?
Yes.
No.
No.
And it's what? What else is gravitational potential energy depend on?
Velocity.
Height.
Guys, come on. Height. So as its height goes up, what's happening to its potential energy?
Goes down. Or no. No. Yes.
It's potential
Okay, I'm
energy.
going to ask it one more time. I'm going to ask just Tiana. Everyone else be quiet. As it goes up, as its height gets higher, what's happening to its potential energy? It's going up. Good.
We said
It's going up. So where would it have the most potential energy? In this path, where's it going to have the most potential energy?
At the
The
very
very
top.
peak.
How much kinetic energy should it have at the top?
Like, a lot.
No, it should
Should
have
none.
close to none.
Yeah, none, and so it's got a very tiny or non-existent K, possibly even 0. When it first started, what's true there? It's going to have both the least potential energy
Yeah.
and the most
Kinetic.
kinetic energy. And as it goes, it shifts, and then it has the most potential energy. And then right about here, when it's right about in the middle, what should it have?
The
most,
more
uh,
kinetic energy.
Most.
It's probably about equal. Probably about equal. And then it'll go back down to mostly kinetic. I left a little bit of you here because I'm saying it's a little bit off the ground. Right through it from not the exact ground. What? Okay, so what's true of the kinetic energy here? What's true of the kinetic energy here? What's true of the kinetic energy here and here? They should be
The same.
the same, as long as we negate friction. In reality, it would be slightly lower here because there'd be a little bit of thermal energy. The ball would be a tiny bit warmer because it had friction with the air. Not enough to notice, and not enough even to measure with the most sensitive instruments, but it is true. But that's why, and then if it actually landed, if it wasn't caught, which it probably isn't here, let's be honest, if it wasn't caught, how would the energy be released down here? It just keep going forever? Well, according to Newton's law, it would, except for that there's
The normal
friction, bounce, a bounce, which would cause everyone misses this one, but that causes a sound, which is energy. So some of this energy would be released as sound, some as deformation. This ball would, you don't really see with a football in real time, but if you watch a slow-mo video of a football landing, you can see it would kind of get squished, and then it would expand back, that's bouncing. And then it would turn into a little bit more kinetic energy, it bounce, and then a little bit more potential energy. And that would happen again, and each time it would be a little bit less because of the friction. And eventually it'll all be friction, lost to the universe.
Wow, that is sad.
Do you have questions about how to, let's go backwards. Do you have questions about how potential and kinetic energy change in projectile motion?
No.
Do you have questions about how kinetic energy is calculated? Do you have questions about how potential energy is calculated? Do you have questions about the kinds of energy?
No.
Do you have questions about energy transformations or transfers? Okay, I'm going to trust that that's all true.